Look at the data on IT project delivery, and the picture is grim. 67% exceed their original timelines by at least 20%. When a deadline slips, project managers try to absorb the delay by scrambling to add buffer time. But using time reactively is just damage control. Placing it proactively, long before the work begins, is a deliberate engineering decision. In this tutorial, we will walk through the 5-phase buffer model. You will use this systematic approach to take an optimistic task list and engineer it into a mathematically resilient schedule. To get started, open your preferred scheduling software and pull up your work breakdown structure. Every manager plans for the work itself. By shifting our focus to explicitly plan for uncertainty, we can build time into the system before it fractures, preventing a schedule collapse before your first deadline even has a chance to slip. Step 1 is granular decomposition. Look at your work breakdown structure and break down the larger deliverables until no individual task is longer than 3 days. This diagram shows the PERT formula, which we use to eliminate the single point illusion, where teams only plan for a perfect scenario. Instead of a single guess, assign an optimistic, a most likely, and a pessimistic duration for each task. Then divide the total by 6 to calculate a weighted average. Replacing single-point best guesses with this calculated average improves schedule accuracy by 34%. Now that we have accurate baseline durations, we need to assess risk. Instead of slapping a massive lump sum buffer at the very end of your project, classify every single task into one of 3 distinct risk tiers. This matrix maps out the buffer you need based on complexity. Tier 1 tasks are routine, getting a 10% buffer. Tier 2 tasks involve external dependencies, earning a 25% buffer. Tier 3 tasks carry high regulatory risks, requiring a 40% increase. Go into your scheduling software and embed those specific percentage increases directly into each task's duration. Do not leave them as side notes. By forcing these buffers down to the granular, task level, you require your team to acknowledge specific risks up front. This prevents them from prematurely burning through a generic safety net months before the critical work begins. Next, map out all task dependencies and resource conflicts in your software to identify your project's critical chain. Warning tone. Here, we have to watch out for student syndrome. This is the psychological tendency for teams to procrastinate and waste their localized task buffers simply because they know the extra time exists. This Gantt chart simulation demonstrates how to solve that. Take the individual buffers you just calculated for tasks on the critical path, strip them out, and consolidate them into a single project buffer placed at the very end of your schedule. Then, at junction points where non-critical sequences merge into the main chain, insert feeding buffers to protect against delays. Throughout this process, you must explicitly label this structural float. Float is the mathematically legitimate slack in your network diagram, whereas padding is just a cosmetic, arbitrary gap between milestones. When a schedule clearly visualizes true structural float, teams understand its purpose and use that time defensively. When they only see vague padding, they consume it carelessly. Now, open your calendar. Hard code mandatory review sessions to trigger at exactly 20%, 50%, and 80% of the project's total elapsed time. During these checkpoints, you will measure one specific metric, the percentage of buffer consumed against the percentage of the schedule completed. If your buffer consumption is outpacing your progress, you escalate the issue right then, using hard data. Looking at this chart of the total project reserve, you can see the required governance boundary. 70% is your contingency reserve, controlled by the project manager. The remaining 30% is the management reserve, explicitly controlled by the sponsor for unknown events. Before kickoff, write out response plans for your high-probability risks, document the exact trigger condition, assign a response owner, and estimate the time cost. This spreadsheet is your buffer consumption log. Whenever a risk actually fires and you draw from the reserve, log the trigger risk, the task name, and the actual time used against your initial estimate. Separating your reserve budgets and pre-authoring these responses means that when a risk activates, your team executes a plan instead of starting a conversation. This eliminates the 1 to 2 days of decision lag that often compounds a minor problem into a week-long schedule slip. You started with a fragile task list built on best guesses. You now have a mathematically resilient timeline. Your tasks have defined risk tiers, your critical chain is protected by consolidated buffers, and you have clear escalation rules in place. The data proves the value of this architecture. Projects that implement formal buffer strategies finish on schedule 2.3 times more often than those that don't. And the buffer consumption log you just created serves a purpose far beyond this single delivery. It becomes a highly accurate calibration dataset for every single project you plan next. Teams that maintain this historical log estimate subsequent projects with 15 to 25% greater accuracy because they are relying on the reality of their own past performance rather than vague industry averages. Implementing the buffer model is undeniable front-loaded work, but it is precisely this proactive engineering in month 1 that prices in and eliminates the crises your peers are scrambling to manage in month 6.